In the coming few slides, we will derive a formula to calculate the equivalent or total resistance of a parallel connection of resistors. But now let's recall the Ohm's law first. I is equal to V over R. In a parallel connection, the same voltage is applied to each resistor. So we can apply Ohm's law, I equal to V over R, to calculate the current going through each of this resistor. I1 will be equal to the Vs divided by R1, this one. I2 will be equal to the Vs divided by R2, this equation, and similarly for I3 and I4. IT is the total current flows out from the voltage supply. RT is the equivalent or total resistance of these parallel resistors. Apply Ohm's law to RT, we can find the total current IT is equal to Vs over RT, where Vs is the voltage of this voltage supply. IT is the total current flows into node A, while all the other current flows out from node A. By Kirchhoff's current law, IT is equal to the sum of these four currents. Using Ohm's law, IT can be expressed as Vs over RT, I1 can be expressed as Vs over R1, I2 is Vs over R2, and so on. Since Vs is the common factor, we can cancel it, and we have this equation. In general, if there are n resistors connected in parallel, 1, 2, 3 until n, then the equivalent or total resistance can be calculated by using this formula. Take note that this is not exactly the total resistance. This is the reciprocal of the total resistance, which is equal to the sum of all reciprocals of individual resistances. It is not difficult to derive from this formula to two important concepts. Firstly, when more resistors are connected in parallel, the lower the total resistance. Secondly, the total resistance is always smaller than the smallest component resistance from this group. Resistance is equal to voltage over current. In a parallel connection, the voltage is a constant. Therefore, resistance is inversely proportional to the current. More the resistor connected in parallel, more the branch currents. More the branch currents, higher the total current. Higher the total current, lower the total resistance. So we have explained the reason for the first point here. Let's say that R1 is the smallest resistance. Then I1 is the highest branch current. Because the total current is greater than the highest branch current, therefore, the total resistance RT is less than the smallest component resistance. So we have just explained the second point. Let's look at some special cases in parallel connection. When only two resistors are connected in parallel, R1 and R2, the total resistance can be calculated by this formula. Using the common denominator R1 times R2, we can rearrange this formula to be in this form. This form can be very handy because it gives us the total resistance directly, rather than give us the reciprocal of the total resistance. Another special case, when n resistors all having the same resistance R connected in parallel, the total resistance is R divided by n. So you can see that the resultant or the total resistance is actually smaller than the original resistance. Special case of this, when two resistors of the same resistance are connected in parallel, the total resistance is half of its original resistance. Remember this, we quite often need to use this. Example 2. In this example, you are required to work out the equivalent resistance RT and the total current IT and the branch currents I1 and I2. The total resistance can be found out by applying this formula. The data R1, R2 is given in the circuit diagram. Substituting them in, we can solve RT to be 90 ohms. The currents can be found out by applying Ohm's law. The total current is equal to the total supply voltage over the total resistance RT, 90 ohms, so it can be worked out to be 220 milliamperes. While I1 and I2 also can be found out by Ohm's law. This Vs 20 volt is actually applying across both resistors, R1 and R2. So 20 volts divided by 120 ohms is this current I1. Mathematics shows is 167 milliamperes. Similarly for I2, 55 milliamperes. We can check out whether the calculations are correct by applying the Kirchhoff currents law. Add up these two currents, which are leaving this node, should be equal to the total current entered into the node. You work it out, you'll find they are equal.